What's up guys, welcome back to a brand new academic video. In this video, we are going to be starting a new series on real analysis. So to give a bit of background on this, I've been wanting to learn real analysis for a while, and I got this book by Terence on analysis, so I was like, hey, why not make a video series on this? Now hopefully this will be beneficial for both me and you, because I'm coming from your perspective. I know what may be hard for first-time learners or what may be challenging. So if it's hard, I'll probably just try to explain it a little better. Also, another thing is that this is going to be a little harder than my normal series. My normal series are usually on high school math, but analysis is college math. So I'd recommend that you'd at least have a familiarity with calculus before going into this. If not, then just try to see a few videos and see if you understand it. And if you don't understand it, it's probably because of the prerequisites and not because you're not understanding it properly. All right, so let's get into the introduction. So the first chapter is going to be on what is analysis. So previously in your career, you've probably done computational mathematics. So computational mathematics. So what is that? That's where you're saying, hey, given this, give me an answer. So computational mathematics is very answer focused. You want to solve for x, you want to factor this quadratic, you want to take the derivative, you want to find this integral. And you start doing computational mathematics when you first enter school, so kindergarten. And you stop around calculus. I mean, technically, it's debatable, like linear algebra, differential equations. The first courses of those are technically computational, but as you get higher up, they're going to start to become more proof-based, which is the second kind. So let's write out proof-based here. Now, proof-based mathematics, you don't usually see until college. So some colleges have a proof course, a mathematic proof course that you take, but a lot of the times, your first real course in proof-based mathematics will be real analysis. So that's why real analysis is often very hard for undergraduate students, because they're it's a very new concept. Previously, you've done computational mathematics, but now you have to rigorously break down everything into proofs. Now, technically, you did do proofs in geometry, but those proofs didn't go into much depth, and they didn't really get into the nitty-gritty of it. So, previously in math, when your teacher gave you some theorem, they probably didn't explain where it came from at all. And even if they did give a proof, it's more of an explanation and not really a rigorous proof. So this should be true, or the reasoning for which this is true is, but you're not really going from step one and saying, why is this true? So you're going to see in real analysis, we're really going to get into the nitty gritty. The first few chapters are going to seem really simple, but they're not going to be easy because you're really going to have to focus and think about these things. Literally, one of the proofs in the book is why 0 is not equal to 4. So that's how in-depth we're going to be going. All right, so let's read a few things from the book here. So Terence is saying that analysis is the rigorous study of mathematical objects with the focus on trying to pin down precisely and accurately the qualitative and quantitative behavior of these objects. All right, so a few key words to mention here are rigorous. So we want to be as rigorous as we can. We're not going to let anything slide past us. There's not going to be any hand-waving in this course. Study of mathematical objects. So by mathematical objects, what he's talking about are vectors. Let's say you can talk about waves, you can talk about functions and things like that. And with the focus on trying to pin down precisely and accurately. So when we're focusing precisely and accurately means we want to have factual information. So you can have a proof that's very accurate, but it may not be very precise. By precise, we want to get into the nitty-gritty of things. So we want to get into the nitty-gritty while being accurate. And qualitative and quantitative behavior of these objects. So basically what that's saying is that we want to understand what these things are from a numbers-based perspective, but we also want to understand what they are intuitively. What is their purpose? All right, so now that we know what analysis is, let's focus on real analysis, which is specifically what this book is about. So real analysis is the theoretical foundation which underlines calculus, which is the collection of computational algorithms which one uses to manipulate functions. All right, so when you get into undergrad real analysis, which is what this book is about, it's usually just going to be, it's sometimes called advanced calculus or real variables. This is because undergrad real analysis, you're not really going to learn new math. It's more like proving your old math. Once you get into grad school and higher level real analysis, you can do things like measure theory, Lebesgue integrals, and things like that. So in general, I would say real analysis is just analysis on real numbers, right? But in this undergrad real analysis course, it's more going to be about advanced calculus. Now, I'm not actually sure if they're going to cover more grad real analysis in this, but I'm assuming so because this is an honors real analysis course. So there probably is going to be a little bit of grad real analysis. But of course, we're going to start with undergrad analysis first. Now, there's other types of analysis as well. There's complex analysis. I don't know how to write the complex number symbol. There's harmonic analysis. There's functional analysis. There's many different types of analysis. In fact, most of math is just analysis once you get into higher level math. All right, so here are a few of the types of questions we're going to try to answer in this course. So the first is to answer some questions regarding the real numbers. So first, the most basic question, what is a real number? We can do better than just a point on the number line. There's far more rigorous and precise definitions from real numbers. Also, what are some properties of them? Why can't we take the square root of a negative number? What is the smallest positive real number? So think about that. The smallest positive real number. So it's above 0. So 0.00000 ... Is that even a real number? Well, we'll see. Is there an infinite amount of real numbers? If so, there's an infinite number of natural numbers, and there's an infinite number of real numbers. But is there more real numbers? Well, it seems so, but is there really? And also, between any two real numbers, there is another real number. What does that mean? How can we use that? Can real numbers keep getting split on infinitely and infinitely? Can we do that infinitely? There's lots of questions to answer about real numbers. The next thing we're going to be focusing on is limits. Now, this means both the calculus-based limits and also what happens when you take things to their limits. If you have a limit of a function, what does that mean? What does it mean for a sequence to converge? What does it mean to diverge? If something doesn't go off to infinity, does it converge? Also, what happens when we take infinite sums? If we take the sum of infinitely many real numbers, does that have to give us infinity, or can it be another real number? If we take the sum of infinitely many rational numbers, will that give us another rational number? Or also, if we take the infinite sum of something, if we rearrange that sum, does it still give us the same thing? Do the properties of algebra hold on infinite sums? So we really want to take things to their limits here. We have to check every boundary. Remember, we're not going to go away with hand waving here. We can't just say, oh, this doesn't work as we go into infinity. We have to answer why. When does this hold? All right, and the third thing we're going to be answering in this course is going to be functions. Now, functions are going to be more in line with what we did in calculus. What does it mean for a function to be continuous? What does it mean for it to be differentiable? What does it mean for it to be integrable? What does it mean? Like integrable, you know what I mean. We want to cover things like the mean value theorem, the extreme value theorem, the intermediate value theorem. We also want to see what happens when we sum infinitely many functions, like Maclaurin series, Taylor series. And when we take that infinite series, what can we do with that? Is that also integrable? If we sum infinitely many differentiable functions, is that sum also differentiable? All right, so here are a bunch of things on what is analysis. So maybe okay, I understand what's analysis, but I still really don't get the point. Why are we caring about these things? In that case, we have to enter into a new chapter, which is why do analysis? So the main reason Terence gives for this is that if you don't do analysis, you're going to run into a lot of mistakes. When you apply a formula without knowing its purely rigorous proof, you don't know when it holds. You don't know if you make a mistake by doing a boundary error. Like, if we let things go to infinity, does the theorem still hold? So let's give a couple examples on when you might be making a mistake by doing this. So our first example is going to be division by 0. Now, this is pretty common, right? If we have a times b equals c times b, what we know is that a equals c. Why? Because of the property of division. So if you have 1 times 0 equals 2 times 0, does that mean 1 equals 2? Well, of course not. You can't divide by 0. Everyone knows that. So this is one example of where our properties don't hold up. There are many more examples. Not all of them are going to be as obvious as this. So let's give another example of when the properties that we usually learned don't hold. So let's look at some infinite series right here. So let's consider the infinite series S equals 1 minus 1 plus 1 minus 1 plus 1 minus 1 ... So it basically alternates between adding 1 and subtracting 1. So if you took calculus, you might look at this and saying, well, this is going to blow up to infinity, so it's not going to diverge. So does that mean that it converges to a number? Let's see. If we take the sum right here, we can think about this as just grouping it. So 1 minus 1 plus 1 minus 1 plus 1 minus 1 ... to infinity. So when we do this, we can simply get 0 plus 0 plus 0 to infinity. So is this sum equal to 0? Well, maybe it's not. Let's rewrite this. So we take this as 1 minus 1 plus 1 minus 1 plus 1 minus 1 ... So instead of grouping it like this, let's try grouping it another way. Let's rewrite this as we have our plus 1 at the top, but instead of subtracting 1, we add negative 1 plus 1. And then again, we're going to add negative 1 plus 1. Then we add negative 1 plus 1. So we're doing the same thing here. We're alternating between plus 1 and minus 1. So it's the same sum. But in this case, you get 1 plus 0 plus 0 plus 0 ... So in this case, s equals 1. So we're getting two different results, s equals 0 and s equals 1. Now let's take this one step further, because we can actually get a third result from doing this. So let's rewrite it again. S equals 1 minus 1 plus 1 minus 1 plus 1 minus 1. So we can rewrite s as s equals 1 minus, and we're basically factoring out a negative. So instead of it being minus 1, it's going to be positive 1. So 1 minus 1 plus 1 minus 1 plus 1 minus 1 ... So if we distribute the negative, we get this right here. So minus 1 plus 1 minus 1 plus 1. But if you notice something here, this whole s term right here is the same as this s term. So we can write this as s equals 1 minus s. And now, solving this will give us s is equal to a half. So is it equal to a half? Well, is it equal to 0? Is it equal to 1? Which one is it? So even though we're doing these rules that we learned, the first one is basically just the associative property. The second one is also just the associative property. The third one you may have learned when you're solving like repeating decimals. If you have like x equals 0.3 repeating, you can multiply both sides by 10 to get 10x equals 3.3 repeating. So you get 10x equals 3 plus x, and then solve for x. So we're each using properties that we know and we know are true, but we're getting different results. Now you may be able to tell that there is an error, but pinpoint the exact location of that error. So even though we might know there is an error, what's causing the error? These are the questions we're going to be answering. All right, so for the next example, we're going to be making a grid. So let's go ahead and just draw in a 3x3 grid. So let's say we see this 3x3 grid in the middle, and we fill this with numbers. 1, 2, 3, 4, 5, 6, -10, 13, actually let me just do 3 again, and 7. And let's say we want to find the sum of all these numbers. Well, let's say one way to do it is just to find the sum of all the columns. So 1 plus 2 plus 3, that's 6. 4 plus 5 plus 6, that's 15. 3 plus 7 plus -10, that's 0. And then we sum all of these individual sums. So 6 plus 15 plus 0 is 21. Now another way to find the sum is to sum all the rows. 1 plus 4 plus 3 is going to be 8. 8. 2 plus 5 plus -10 is going to be -3. 3 plus 6 plus 7 is going to be 16. So you have 8 minus 3 plus 16, which is also 21. So it doesn't matter if we sum column first or row first. We're going to get the same sum either way. And this kind of makes sense, right? This is just the associative property. 3 plus 6 plus 7 plus 2 plus 5 plus -10 plus 1 plus 4 plus 3. It's the same thing as 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 3 plus -10 plus 7. Now, if we apply that to infinity, it might not always give the same result. Let's make more columns and more rows. So let's do the same thing here. So let's go over this quickly. So our first row, our first column is going to be 1 minus 1, 0, 0, 0, up until, it goes on forever. Oh, I should probably add, this goes on forever to the right as well. Then the second one, we're essentially going to add an extra 0 on top, but besides that, it's the same thing. The third column, we're going to add 2 zeros, but besides that, the same thing. Fourth column, 3 zeros, then the same thing. So each extra column, we're just adding an extra 0 on top. So let's take the sum of all this. So let's take the sum of the columns first. 1 minus 1, then goes on to infinity with 0, so that's just 0. Same thing, we're just adding an extra 0, so also just 0. 0, 0, 0. And this is going to go on forever to the right, so it's all going to be zeros. So the total sum is going to be 0. Now let's take the sum with the rows. 1, 0, 0, 0, and this is going to be zeros forever. This is going to be 1. Minus 1, 1, zeros forever, 0. 0 minus 1, 1, zeros forever, 0. Minus 1, 1, zeros forever, 0. Minus 1, and there's going to be a 1 here, zeros forever, 0. So this is also going to be zeros forever. But we have an extra 1 here. So this sum, if we sum all the rows, it's going to be 1. If we sum all the columns, it's going to be 0. So you have two different sums here. So what went wrong? Does the property of association just not hold when we have an infinite number of items? Well, we'll see later in the course. All right, I have 2 more examples for you that are going to be more focused on actual math here. So let's say we take L equals the limit as n goes to infinity of x to the n. All right, so let's say we have x equals 0.5. So as n goes to infinity, we have 0.5 to larger and larger numbers, which is going to make it smaller and smaller and smaller. So that limit will be 0. So one thing we can do with limits is, just for fun, let's just change the variables. So we're just going to change the variables and say m plus 1 equals n. Now this is something we can do. Variables are just something we define after all. So why can't I change them? There's no reason not to. So we have x to the m plus 1. We can use exponent properties, right? So as m plus 1 goes to infinity, this is going to be x times x to the m. So we can take x out of the limit because it's not going to, it doesn't depend on m. So you take x out of the limit, m plus 1 goes to infinity. Sorry, plus there. And x to the m. So one thing we notice is that as m plus 1 goes to infinity, m also goes to infinity. So we can write this as the limit as m goes to infinity of x to the m. So why we can do this? Well, let's say m is going larger and larger and larger. So let's say m is going to be 999999999. So then m plus 1 is just going to be 100000000. So as we go higher and higher, it doesn't matter if m plus 1 gets larger or m. Because 1 makes such a small difference on those large scales, it doesn't matter which one goes to infinity, m plus 1 or m. We're going to get the same result because the variable are going to be increasing without bound either way. All right, so now that we have the limit as n goes to infinity of x to the m, one thing we can do about limit is it doesn't matter what the variable is, it's still going to be the same. So if I change m to n, it's still going to give me the same result. Why? Because when we change variables, it really doesn't matter. It's just a variable either way. So it doesn't matter as m goes to infinity of x to the m. It doesn't matter as n goes to infinity of the x to the n. It's the same thing. But what we notice is that this limit right here is the same as our original L. So we can substitute L for that. So L equals x times L. So one thing we can do here is move xl to the other side and factor. So you get L minus x times L equals 0. So L times 1 minus x equals 0. So the zero product property tells us that L equals 0 or x equals 1. So what does this mean by that? Well, what it means is that if we take L equals the limit as x to the n of x to the nth power, x to the goes to infinity of x to the n, what this really means is that either this limit equals 0 or x equals 1. So if x is not equal 1, let's say x equals 2, then the limit equals 0. Sorry, this should not be x right here. This should be n. So what that tells us is that it doesn't matter if x is 2, 3, 4, as long as it's not 1, this limit is 0. So 2 to the n as n goes to infinity, that's 0. 3 to the n as n goes to infinity, that's 0. But this is obviously not true. The limit's not 0, it's infinity. So where did we make a mistake here? All right, so let's end this off with our last example. So our last example is going to be if we take the limit as x goes to 0 of x squared times sine of x to the minus 4 divided by x. So let's take the limit as this approaches 0. So the bottom becomes 0 and the top becomes 0. So this is going to be a 0 divided by 0 form. But what that means is that we can use L'Hopital's rule. So let's go ahead and apply L'Hopital's rule. So write the L prime h here. Take the limit as x approaches 0. Take the derivative of the bottom and the derivative of the top. So this is going to be x squared of sine of x to the minus 4. All right, so once we do this, we can still write limit here. Derivative of x is just 1. Derivative of the top, we're going to be using product rule. So left, derivative of the right, derivative of sine. Actually, I'll just write this as derivative right now, and then we'll do it in the next step. Times, or plus right, derivative of the left. Derivative of x squared is just, well, I'll just write it out as the derivative for now. All right, so let's complete this. The 1 doesn't really mean anything, so we can make that go away. And so we have x squared. Derivative of sine of x to the minus 4 is cosine x to the minus 4 times minus 4x to the minus 3. And then we have a plus sine x to the minus 4. Derivative of x squared is going to be 2x. Sorry, this shouldn't be minus 3. This should be minus 5 because we're subtracting 1. So this should be minus 4x to the minus 5 here. So now we can combine exponents to get x goes to 0. Minus 4 x to the minus 3 means that what happens essentially, 3 is going to be in the denominator. And then this is going to be 2x sine x to the minus 4. Minus 4. All right, so let's try to evaluate this real quick. So if we plug in 0 for this first term, because there's an x cubed at the denominator, as that gets closer to 0, this gets closer to infinity. Now you may be asking, wait, what about the cosine? Well, to deal with the cosine, we can use the squeeze theorem, which still gives it infinity. I'm not going to do this like on paper, but you can do it if you want. Anyway, if we plug in 0 for this is also going to give us 0. And you may be asking, wait, what about the sine? Well, again, squeeze theorem also makes it 0. But either way, the sine's not going to have a significant impact. It can either be in between 0 and 1, and any number is not going to change the fact that this goes to 0. So this limit is infinity. But is it true that this limit is infinity? Well, let's look at Desmos. So you can see here that this is our original function. This limit goes to 0, not infinity. Okay, so why did it say infinity? Maybe it's a problem with our L'Hopital's rule. Not the problem with our L'Hopital's rule. Maybe we just didn't evaluate this limit correctly. But nope, this limit does go to infinity. So the only room for error here would be the step that connected these two, which would be L'Hopital's rule. So does L'Hopital's rule not apply in this instance? Well, we'll see later in the book. So some of these examples may have been more obvious to see where the errors were. There are a bit more subtle examples in the book, but I didn't want to cover them because we wouldn't figure out the answers until later. So maybe I'll make a part 2 of this video, just giving some more examples of this once we get later on into the course. So those are the practical reasons why we should do analysis, because it helps us spot our errors and make sure we're not making mistakes. But I feel like if we're just doing analysis for the practicality, then you're going to get frustrated at it, because it's a lot more than just practicality on why we take analysis. The reason why we do analysis is because of the satisfaction of knowing why things are true. Now, when we think of math, what's the one thing that characterizes math from different subjects? What separates math from science or history? Well, the thing is, the only thing that's special about math is that we know things for purely rigorous truth. In science, we can do experiments to see things that observe to be true. They're probably true, but we can never get things with 100% certainty. Math is one of the only subjects where you can say, if my hypotheses were true, then using this logical reasoning steps, I can figure out that the conclusion is true. And that's just really satisfying in my opinion. So if you're asking yourself, why should I do this? Then just try to take a step back and try to just enjoy the math for what it is. You're not going to have a good time in analysis if you keep applying that mindset that all math has to be useful for something. I have to apply this into the real world. Sometimes it's just fun to do math for fun, to do math for your own sake. That's the whole point of pure math. So even though there may be practical applications, I think the real reason why you should do pure math is for the joy and beauty of doing math for its own sake. Thank you for watching this video of academic learning. As I said, there's going to be more videos in the series, so if you have any questions, comments, or concerns, please leave them in the comments down below, and I'll see you in the next video. Bye!